In this section, we're going to dig a little bit deeper into hypothesis testing and the conclusions that we can reach. So first, we have to just remind ourselves of some definitions that we've been talking about. Hypothesis testing is that formal process to test an accepted or a believed claim about the population. The significance level, alpha, is the probability of making a mistake and rejecting the null hypothesis when in fact the null hypothesis is true. And alpha equals 0.05 is the most common. Although they can change that, you can choose to change that if you are the researcher, and that can be left up to you, but 0.05 is the most common. The rejection region is the region in the tail or tails of the normal curve that has an area equal to alpha. If a test statistic falls into this rejection region, then there's strong enough evidence to reject the null hypothesis. The critical value or values are the number of standard deviations away from the mean that creates the boundary for the rejection region. You may have one or two critical values depending on the type of test. So remember, you may have only a positive or only a negative critical value if you're doing a one-tailed test, and you could have two critical values if you're doing a two-tailed test. Same thing with the tails. You may have one or two depending on the type of test. So this test statistic is a quantity that represents how much your random sample differs from the parameter in the claim. It represents the number of standard deviations away from the mean under the normal distribution. Z is the test statistic used for tests on a population mean with a known standard deviation. And T is the test statistic used for tests on a population mean with unknown standard deviation. So this is the same idea as when we were creating confidence intervals. If you know the population standard deviation, you can use the Z test. If you don't, then you need to use the T test. Now this might be a little bit new. I don't think we've talked about this yet, so this is new information. The p-value is the probability of getting a test statistic as different or more different from the parameter in the null hypothesis. Okay, so this is a number basically that measures the surprise of your results. A large p-value means that there is a large probability that if you took more random samples, you'd get a result just as or more extreme than the one you just got. So what that's saying is that there's a large likelihood that what just happened in your sample will happen again and again and again. If you keep taking samples, probably what we saw happen will keep happening. Hence, what we saw is not very surprising. If it's likely to happen over and over, we're likely to get the same type of results over and over, then we're not very surprised by what's happening. However, if you get a small p-value back, what that means is that there is a small probability that if you took more random samples, that you'd get a result just as or more extreme than this one. So it's unlikely that what we just saw would happen again. Hence, what we saw is very surprising. Okay, if what we saw maybe was a fluke, let's say. We saw a result, but it's very unlikely that that would happen again, or something more extreme with that than that would happen again. So maybe we chalk this up to just being kind of a random fluke. It was an accident, and it's not going to happen again, most likely. So it was a surprising result. Another way, or the p-value, is another way to decide whether to reject the null hypothesis or not. You compare this p-value to the alpha that has been set. If p is less than alpha, you are surprised and you reject the null hypothesis. Remember, when we reject the null, that means that there is enough evidence to support the alternate claim. However, if P is greater than alpha, we fail to reject the null hypothesis. We conclude that there is not enough evidence to support the alternate claim. And then, of course, we always follow those conclusions up with what this means in the context of the data. So this is another way to solve these, or to finish up these hypothesis tests. So you can either use the rejection region, and you can either find and look, at the image, does my test statistic fall in the rejection region? Or without having an image, you can say, is this p-value less than alpha or greater than alpha, and what do I do? And you should reach the same conclusion no matter what. They work together. It's just two different ways to look at it. Students have a hard time, or what I've seen is that students sometimes have a hard time remembering what to do when. Like, what do I do when p is less than alpha, and what do I do when p is greater than alpha? How do I remember when to reject and when to fail to reject? So these are some ideas that I think can help you remember. There's a funny little sentence that you can say, which is that if the p is low, the null must go. So that's this top situation right here. If your p is low, the null must go. If p is less than, we reject that null, okay? Also, just the simple idea that when you have that smaller p, you're going to have a shorter sentence. So when p is less than alpha, that's your small p, then you have the shorter sentence, which is just simply that I reject the null. Very short and sweet. But a larger p-value results in a longer sentence, which is the fail to reject scenario. So we fail to reject the null in that case. And that can kind of help you to remember what to do when.